Hey everybody, this is Time Travel Beard, and in this episode of How to Make Shaders, we are going to go over compute shaders, and we're going to use them to do some different effects that are kind of just for fun, and show us how compute shaders work. One of them is we are going to have slime, like all over the ground where the slimes go, so they make a mess, and these patches will slowly fade over time. Another one we're doing is we're having a shoreline detection, where we're detecting where water is, and having a gradient come out into the ground. And then the third effect we're doing, probably the first one, is kind of like a floodfill like you'd use for colored lighting, where we're going to have gold blocks emit an area of light around them that fades at the distance. It should be fun, and should be interactive. I wrote this whole thing a few days ago to make sure I'd have it good as a reference, and then we are going to try to rewrite it so that we can go over some of the bugs and stuff I had along the way, so that you can see how to tackle those in case you run into any, and kind of have a deeper understanding than just copying code. But I've got the finished code there also as a reference for us, so that we can go back to it and kind of do things quick and not take an hour on this, hopefully. So first thing is, let's get into the concepts of compute shaders and what they do. So for our concepts, we're going to first look at what are shaders in general, and they're just a program that runs math on stuff. We already went over our vertex shaders, where they take in a vertex or a dot that's in the corner of a square, and they do math on it and decide where to put it on the screen. So in those, we have like a vertex coming in and a vertex coming out, but the vertex coming out had the attributes that we gave it, such as color and lighting and textures, coordinates and stuff. Our fragment shader then took in every vertex, and it well, there's a kind of geometry trade, I guess, in between those. But there's stuff that happened there where we had that vertex information. And then our fragment shader runs for every pixel of the face. So it takes in that pixel or fragments data that it got from the vertex by mixing the three vertexes together and blending where it was in the middle. It runs for every fragment, and it does output to the screen into whichever textures we drew. So we might have it put out a color. We might also have it put out like normal map detail or PBR texture data if we're doing a deferred rendering system and not just doing other colors right away. So one runs for vertexes, one runs for fragments or pixels. What does a compute shader do? Well, it runs for whatever you want. It does whatever you want, and it outputs to whatever you want. So it kind of lets you do whatever you want. So what would you want to do with it? Well, we already talked about composite shaders, I hope. Yes, because we use those to draw our clouds. Which, if you have not watched the voxelizing tutorial, I would recommend watching the voxelizing tutorial, because this is built in off of the voxelizing tutorial. Because two of the things that compute shaders are really good at is processing an image that is not screen space. It's just some other image we have to do, because our composite shaders already run over the whole screen, and they're just a fragment shader that runs for that rectangle. But what if we had a rectangle that wasn't screen sized, a texture that wasn't screen sized, and we wanted to blur that or something? Well, that's one example of what a compute shader is good for, is it could run for this other texture that's some weird size. Or what if we have a 3D area like our voxel data, where we voxelize stuff, and we want to do things on that to do something like colored lighting or the effects that we showed today. That's something a compute shader would be really good at. So how do they work? Is the main things we've got to work on is defining our inputs, what we want to do, and defining our outputs. With our inputs, it's pretty much we're going to load voxel data, but we also have to define some parameters for the compute shader, which is work groups. This is the only thing that's probably kind of confusing about them. So if we look at a GPU, the way it draws things normally is it's got multiple cores, whereas a CPU might have 4 or 8 or 16 or 32 or whatever. A GPU has like hundreds. But it doesn't have enough to do the whole screen at once, because the whole screen is millions of pixels. So it breaks things down into chunks, and it does a chunk at a time, called like a work group. And when games get slow, a lot of times it's because Each work group runs together, which is why we generally don't want to do branching code. And it does like one chunk of the screen at a time. With a compute shader, it's still doing one chunk at a time, but it's going to be doing chunks that aren't pixels on the screen necessarily, but whatever we want. What we're going to do is we're going to imagine that these threads are this little dude right here. So when you've got little dude, he's not alone. He's in a work group. He's got buddies. And all these little guys, they work together. So these 4 guys, they're a work group. Actually, let's make it a little different. We're going to say that there's more guys. We're going to stick them like this. This group, they do everything together. So whatever it is they want to do, they're going to do it together. That's just how it is. They're faster that way. They're more efficient that way. They're a core. They're a group. They're a work group. And whatever they do, always do it together. So if you have branching in your code, the reason that's bad is because these guys are going to do everything that they do together at the same time. So if you tell them, we're going to arrange them in a cube, this is their little work group box. They like to stay in formation, in this little formation. So if you have code and it goes down and says, if do this thing, if we're one thing, if a pixel hits some other things, do another thing. And you've got all this code here and all this code here. When this work group comes down, they're going to stop together and all do this, even if some of them don't have to for their pixel. And the ones that don't have to do it are going to wait while the other guys run this whole complicated path and come back. Then they're going to go down to the next part. And even if only one guy has to go down this other path, we're going to wait for him to run down and do all this code inside of that if. And then they're going to go down together. And they do everything together. Which is why for branching in code, you generally don't want to do it because you've got guys just waiting around in a work group. You want to keep things as coherent as possible. So that's what work groups are, is it's just a group of threads on the GPU that do things together. But in compute shaders, we get to actually define how big this group is, and we get to define this 3D formation with our X, Y, and Z components of how big this box is and how many guys are in it. We can say we want 3 guys on the X and 3 guys on the Y, and maybe 1 guy on the Z, 100 guys on the Z. It's whatever you want. Why would we care about this? Well, most GPUs send out maybe 64 guys at a time or 32 guys in a group. So if we tell this work group to only be as 10 blocks, then you've got potentially 54 guys just waiting around here because only 1 guy is doing work and the others are all just standing around. So we want to have full groups of guys, full work groups doing work all the time. So because of the numbers that work out, we generally want to do something that's a number of 64, like a multiple of 64, because if we do say that our group is bigger, we have a bigger chunk of work to do, they'll just split it into 4 groups if they have to, and then do a quarter at a time. So you want your work group number to end up being a multiple of 64. However, the general consensus is to use 256 or 128 because apparently it's easier for the GPU to lay out, like let's say this is 64 in each of these squares. It's easier for it to lay out 4 chunks of work to do as one pile and say, here's your pile of memory. You guys do this, and they do 4 chunks all at once. That's faster for the GPU than having it just do 64, because then it has to lay out a pile of memory each time for each chunk instead of it doing one big group. Even if it only has 64 guys, that chunk of work that's 256 is more efficient because it doesn't have to lay out all this extra scaffolding. So that's kind of what work groups are. But how do they relate to what we're doing and laying out parameters for them? I already said we probably want to do 256, a work group that's 256 guys. If you think there's more branching in your code, You can do a smaller thing. I wouldn't go below 64. And then you've got less guys waiting around if there is branching. But if you're less likely to have branching, just do the 256. Yeah. It's probably the best bet. If not, maybe 128. Test on your machine, and it's going to vary on machines because they have different sizes of groups. Anyway, work groups are generally defined in compute shaders by their size, and their size is three-dimensional. And the way it works is it's going to take this voxel map we have, and it's going to break it up into these groups. So we can make these sizes whatever we want, but we want them to be 256 or 128 for each cube. So if our square here is 128 in one direction, that's already 128. So if we just do it 128 long and like 2 wide and 1 tall, that already gets us the 256, taking a little chunk that's just like a slice like this. Or we could do something that's like an 8 by 8, and that gives us 64. And then how many tall of 64 would make us 256? You know, it's just like a few. So you can slice this up any way you want and process it any way you want. The general idea is just we're trying to get this 3D formation to be 128 or 256 so that we always have groups of multiples of 64, and we're not wasting any. And then the compute shader is going to take each work group, each little 3D formation, and it's going to run it through our data and take out that chunk, take out this chunk, take out this chunk, take out this chunk. Just like how this does vertexes and this does fragments, this 3D work group is going to run around through all of this. Now, if we're not doing a 3D load, we would tell our work group to have an X size and a Y size, but our Z size would just be 1, and then they would just run for like a little plane on the bottom. I hope that's not too confusing. I hope I did good with that. But let's look at some code and look at what this actually looks like. So I've got here a template we're going to run through first, the template version of the compute shader, and then we will also do our actual coding. I'm doing a very cursed thing in running Notepad++ in a virtual machine with like synced storage stuff. If you know a better way to manage that, let me know. We'll manage a better way. So let's look at some of the code in our template. So as I said already, a compute shader is like a fragment of vertex shader, but it runs for what we want. In our work groups here, I already kind of went over the concepts that we've got those groups, but we also have to say not just how big they are, but how many of them there are. That's what I've got to do with the picture. So, so when we define our work groups, not just defining how big each formation is, but then how many formations there are in each direction to fill in that 3D space. So we just have to do that. Here's a little note about sizes written out, and then here's our actual code for the compute shader where we're defining that. So this here, our local size, is the size of the work group. And then the constant i-vector work groups is the amount of work groups. So for this example, we're saying that our size of a work group has each group's local size. It's 8 guys on the x-axis, it's 16 guys on the y-axis, and they're only 1 tall. So they're running as like a 2D tile, where it's 8 guys times 16. And I think that gets us to 128, maybe. It's 80 and 48, yeah. Now, since we have different sizes of voxel areas we can run in our tutorial, we need to have different potential numbers of work groups. So if we're only doing 64, we do an 8 by 8 by 64, because since we're only running one on the Z, to do 64, we'd have to run 64 of these groups. And these numbers are slightly off here, actually. That's not right. So if our group is a size of 8, and we want to do 64, we'd have 8 of them. If this is 16 on that axis, then this would only be 4. And that's how we would fill in that big of a space. If our voxel area is 128, our Z of 1, we would have 128 groups. 8 into 128, you would do that math, and that'd be here. Then 128 divided by 16, that's the number you would put here. And this is put inside of these macros because you cannot define this or constant live-rect3 of workgroups with a macro defined number directly. So we're saying if it's this, do that. If it's this, do that. That's kind of annoying. It's just what you have to do. So our inputs and outputs. This is the other part of the comp shader that you have to spell out. Generally, we're going to take in custom images, and we're going to define them the way that they are defined to be read. As an example here, we've got what a 3D image looks like, both with a 32-bit unsigned integer format, which is what we use for atomics, and then also as an RGBA8, which is generally the format that we use for most other things. We have a red, green, blue, and alpha component. See the difference here is not just here, but then when it's declared, it also has this is view image 3D, this is image 3D. We also could have image 2D, and then we have the name, and this name is the same name that we would have declared in our shader.properties, where we declare, before we already had this image, image1, which also has a sampler name, so we can do it as a sampler. And its format matches. It has read integer data, it's R32uint, unsigned int. I don't know why we've got to spell that out pretty much 3 times, but that's just how it is. And then if you remember in these, it has defined also what it occurs every frame, that the size is relative. So we've got those true and false values, and then there's the size of our voxel area, and that's where these textures are defined. We'll go more into this when we actually do our implementation, because we use 2 different types, and we do some different size things with them. But here's just some examples of how to do that. And again, our sampler is what we would use for interpolated reading of the textures, where it would read and smoothly blend between the values instead of just taking directly on the grid. So for our inputs and outputs, we declared this, which we're saying that we have a 32-bit unsigned integer that's a 3D image with this name. This is as an input or an output. It's both. It's whatever you want. And then we also are declaring our custom sampler, which is a usampler 3D. Those are only for reading. Those are not for writing. And those give us that interpolated smooth blend that we're getting so that it's not blocky writing. In our computer shader, we also then have just our uniforms that we normally get from Minecraft. We are specifically using these 3 because they are very helpful for managing 3D voxels, 3D voxel data. There's a note about shader properties. And then here's our actual compute shader. So let's look over what this template one does, and then we'll get into making our own. So we are going to wrap the entire main function in a macro, a preprocessor to define of whether or not to run the shader, because in Iris, you can have multiple compute shaders per shader, just like we can have composite 1, 2, 3, 4. In each of those, you can have a compute shader. You can have one run for every pass. You can have it do like composite 2A, and then one composite 2B, and then one composite 2C, all the way up to composite 2Z. But if you disable B, then C, D, E, F, and all of them won't run. And that can be really kind of bad if you're doing certain things. So we're going to just wrap this in whether or not to run it, but we have a way to control this better in our settings if we wanted to. First thing we're going to do is we're going to now connect. We've got these work groups that are our 3D cube, and we've decided that we've got a certain size, a 3D formation of a work group, and we've got a certain number of them so that it's going to cover our whole cube of work. But it still isn't actually connected to our texture in any real way. We have to make that association. So what we're going to do is we're going to use this in here, is that we can call GL global invocation ID XYZ, and that gives us the ID of that thread. So for each of those guys has a worker ID number. It's a little badge that says, I'm guy number 1, I'm guy number 2, but it's 3D. So he's like, I'm guy 159 because I work on the x-axis number 1, y-axis number 9, whatever. He's got his spot, and he knows his spot. So we're going to use their knowledge of where they are in the overall run over everything to then assign them a spot in our voxel map. So the way we're going to do this is we're going to say that their voxel position is just their location. That's good. But then for the rest of this, I'm going to draw some more pictures to make this make sense. So we've got our local group size, and then we've got the number of groups is how many fit along this axis, and how many fit along this axis, and how many fit along this axis to get all the work done, because we needed to have a size of a group and a number of groups to work enough to do all of our space. There can be a problem with just doing that directly, is that we have something called a race condition, where if you have our space here, I kind of drew a slant, I was thinking 3D, but I'll just do this 2D. Let's say that with like a Floodfill type example, this block's lighting value depends on the values of the blocks around it. So it needs to read these other areas. It's not just independent, it's dependent on what's around it. So if we wanted something to go to the side one every pixel or something like that, every frame, since it's dependent on what's around it, we can't just read this stuff and write it to the same spot, or we'll get like weird race conditions. I'm trying to think how to quickly think of this. If we wanted a circle to expand once every frame by drawing in every direction if its neighbor was the same color, if we just did that all at once, in our first frame we would have, okay, this one is red, so draw red to all the ones around it. Cool, next frame draw red to all the ones around those. Cool, we get a nice little slowly expanding thing. The problem is, since the work groups run in any order they want, what happens is that if it just does this here, if this one draws here, and then the next group checks that block, it's going to say, oh, there's already one here, so let me draw one to the side. Then the next group that checks this one and say, oh, well, there's already one here, draw there. Then it gets all lopsided, where it's going to draw like all stretched out in this direction, but then do like what we expected in this direction. But then even here, since they're running in any random order they want, it's going to be all glitchy looking and all kind of jacked up, because there's not a separation of the last frame's data and current frame's data. The way that most things do this automatically behind the scenes in Iris is it's got like a main buffer and an alt buffer. So when you read data, it's reading from this one buffer, and then it's writing to another buffer. It's taking twice as much space for everything. So here's where stuff was, and then here's where stuff is going to be. And it just keeps both of this in VRAM. When we're using custom images, it doesn't do that on its own. So we're going to create our own double buffers so that we can read our data of where it was and have completely separate our data of where it's going to be. So we can read from here and say, okay, I want to read all of my neighbors and what colors they were. And then I'm going to write that to this new spot so it's clean data and it doesn't have any artifacts from mixing old data and new data. And we're going to have this kind of a double buffer. We're also going to use this so that when we move, things won't smear, because our voxel map is centered around us as a person, around the camera. So we want to make sure that when the camera moves, we also need to update all those locations, because otherwise something would just smear as we move. I can actually show that really quickly in code by messing up stuff. We'll do that when we get into it. But to make that work of a concept, we're going to have our original voxel position just be the thread ID. We're going to track our camera shift, which we're going to track the current camera position and the previous camera position to get the difference in movement. And we're doing this as ints, not as floats, so that only when the camera shifts from one block to another block, we're going to keep track of that value and say, okay, the camera moved into the next block, so we need to be aware of that so that we can shift all of our voxel positions over. So we're going to have our old voxel position would be the thread ID plus the camera shift, and our new voxel position of where it is relative to us now. It's here. Because if we moved one to the right, then to know what was in a spot last frame, we need to not just look where it is, but look where it was relative to us last frame. So that's where we're tracking our camera shift. And then we're going to do a double buffer. So to do a double buffer, as I said, we need that to kind of keep the data separate. And the way we're going to do that is we're just going, instead of having two separate custom images for this, I think that's kind of wasteful, we're going to take one, and we're just going to make it twice as big on one axis, split it in half. So if this is 0, and this goes all the way to like 100 pixels, or 100 voxels, and we want to have our second pile next to it, we're going to say, well, instead of reading from 0 to 100, we're going to read from 100 to 200. So we're going to just say that that offset is 100, or the offset is whatever size it is, and we're going to just add that offset when we're reading and writing our data. So here, a double buffer offset is going to be 0. It's an IVEC3 because we're using a 3D space of 0. How big our voxel area is, and 0. So we're deciding to push it off on the y-axis, which means that inside of our things here, when we're defining the size, you see this one is 64. It is 128 on one axis, and this one is 32. It is 64 on one axis. We're doubling the size on that one axis to have that. And the reason we're doing this right here, mod frame counter 2 equals 0, is we're saying pretty much if we take which frame we're on of the game, it just counts up 1, 2, 3, 4, 5, 6, 7. That mod 2 is saying if we divide that by 2, how many are left over? It's pretty much saying let's count 0, 1. We're counting to 2. So it's doing 0, 1, 0, 1, 0, 1, 0, 1. So on every other frame, that'll be 0, and then on the other frame, it'll be 1. So if this is 0, we're going to say that we are writing to one spot. And if it's 1, because here it's not 0, our read value is on the other spot. And by doing that, we're just going to constantly go back and forth every frame so that we read from here and write to here. And then in the next frame, we take that new data that we read from here and write to here. We just go back and forth. And doing it that way just means we don't have to like copy this back over every frame when we're done. We just kind of bounce back and forth. It's more efficient. So we have our old voxel position every frame, and we take where we are plus the camera shift, and then we add, and our new one is just where we're at right now. And then we take our double buffer offsets for reading and writing, and we add them so that we're reading from the right spots. I hope that makes sense. It's just something that we're doing. So once we figure out where we're reading and where we're writing, we then can actually load our data and do it. So I've got here some different things you could use for that. We actually do stuff, and then we output our data, which we would have to do image store or image atomic max, something like that, to actually write the data somewhere. So all of this was to say that in our compute shader, we decide how big the local group is. We decide how many of them there are so that we do all of our data. We decide which things we have as inputs and outputs. This one is just an input. We still pull in our data from Minecraft. We can also include our settings files and stuff like that. And at the top, we would need our declaration of version 430 or whatever. And then in our main, it literally doesn't do anything that we tell it not to do. So we were deciding to run it. We are figuring out the index of threads and offsets for our double buffering and our camera movement so that we have a position to read from and a position to write to. And then we would do stuff. We'd load our data, do stuff to it, and output it. So that felt like a lot already. So let's get into an example of actually doing something with this now. Okay, so let's actually make this ourselves now. We're going to try to make this fast because this is already like a half hour in, and I wanted this to be a quick video. So there's a few changes to other files. We'll just kind of look over them real quick. For setup, one of them is that in shader.properties, at the bottom where we declared our cimage1 as csampler, and this is where we were voxelizing to. We're also going to have what we're calling our Floodfill image here. So we're defining cimage2, colored light, so we have a name for it. That's a sampler name, which is also nice and descriptive. It is RGBA8, which is a byte. It does not clear every frame. It's not a relative size. And we're doing three sizes, 128, 64, and 32. On each one of these, the y-axis is doubled for our double buffer. In our voxelizing code, we're going to, everywhere that, we don't have a settings.glsl file in this one. These defines are just scattered. So everywhere that this is, it has to be updated to have 5. And for visualized data, number 5, we are going to do the following. For our Floodfill examples, we are going to have the voxel data, the possibility of a few different things. We're using some ternaries here. So if you remember, when we do question marks, it allows us to do if-then statements in one line. So we're going to do a test for gold, water, and for slime. So our voxel data equals something dependent on these things. If our render stage entities and our entity ID is 1, we're going to set it to a green value of 1. If it's gold, we're going to have a voxel data, and this is defined by block properties. I'll look at both these in a second. We're going to set it as red. If it's water, we're going to set it as blue. We have not done a bit packing and bit work episode yet, so we're just using channels. And for each one of these, after a question mark, if it is this, we do this. And then we have a colon. If it is this question mark, we do this. And a colon is another choice. If it's this, we do this, colon. If it's none of those things, we're going to set it to this value just so there's something there and it's not blank, so that we can check, because something that isn't written to should have a value of 0. So let's look at quickly the other setup. So that's our voxelizing code. That should already be done in the example. We also had made changes. Changes will be there already for you in block.properties. And in entity.properties will now exist and we'll have data in it. So in entity.properties, we're saying that entity 1 is slime. And that's what gives us that slime value. And in our block.properties, we added gold block to number 2, and water to number 3. And inside of our voxelizing, because of that, we had to go into our vertex shader where we're doing voxelizing, and we have to make sure that we are using uniform entity ID, and that's what lets us have that value to tell entity ID, and we also have to use the uniform for render stage, which has preset values like this, which you can look up on the shader.properties website, which is the iris documentation. So our visualized data, now instead of doing those other things, we do number 5. And in our fragment shader, we need to also account for that. There may be some extra stuff we added here, probably frame counter in our gbuffers terrain. And then visualize data. Let's see where that is. What we're going to do is not visualize our voxels anymore by default. Instead, we're going to not visualize to bytes. We're only going to visualize our color to the data we got as our default voxel color if we're not doing visualize data number 5, because visualize data number 5 is our new thing. And then we're going to add code for visualize data number 5. We'll get to this in a second. I want to This will probably all be commented out to start, and we'll go over it piece by piece because I want to show what that does. Oops, I hit the wrong buttons there. So let's so our voxelizing has a new mode to visualize data, and it's probably not going to do anything. Yeah, let's get in and let's start experimenting. So here we are, and we're probably not even on visualize data number 5. So let's go to our settings, go to visualize data 5, see if it does anything. It doesn't do anything because it's just bypassing stuff. So let's look at what we want it to do and what data we want to do. We're going to do it step by step. So first, let's just create a compute shader. So this is writing data that if a block is gold, it should have a value of red. If it's water, it should be blue. If it's slime, in that spot, it should put green. And that voxel data is being written to our image1, the voxel position. So let's create our compute shader. We're going to go in to templates, and we're going to take start here. And our actual compute shader we're going to use has version 430 on the top. We are defining our voxel area and radius here because we don't have a settings.glsl file. There's our local size at 8, 16, and 1, and here it fills in the groups. Our inputs and outputs, we are taking in our image1, which has the voxel data, and we're going to also have our second image, image2, or our colored light is what we're calling this. And that's the one that in shadows.properties we have declared. Let's double the size on one axis so that we have a built-in double buffer. And then in our main, we have severe. I want to add something I forgot to add here, which we can copy from gbuffer's terrain, which is when this checks the voxel data, it makes sure that it's in range. Let's add that to our compute shader. So we've got our original voxel position for this. We'll do it after this spot just so it still looks nice and clean. We'll say if our original voxel position, if clamping that between 0 and voxel area isn't equal to the original voxel position, we don't want to do anything because that means it's out of our range of voxels. So we'll take that and we'll go all the way down here. Just wrap this all up. So indent that. My indentation is not as clean as it usually is on this because I'm indenting based on these comments as well to kind of make it easier to kind of browse through the main idea of load stuff, do stuff, and upper data. And also everything that I do in the final version is commented out here. So, so that, and what we're going to do is we're going to take this start here. We want to save as, and in our main shaders folder where we have all the other things here, there's a program we have not used before called prepare. Prepare runs after the shadows and before the gbuffers. And this is a .csh because it is a compute shader. Compute shaders generally, I believe, run before the vertex and fragment, but because this is its own pass, it doesn't matter. And what is our prepare compute shader doing? It is going to load in our load data and unpack. We're going to make an integer value that loads our voxel data, which if you remember in our voxelizing, the voxel data was a vector, but then we pack it into an integer value here so that we can do atomic max to prevent flickering when we save it in the C image. So we need to unpack it. So just as we packed here with this built-in function in prepare, we are going to load it, and we load just the R because it's a single channel of data. And say our voxel data will be the unpacked integer value. And then we're going to say that our color effect is the voxel data. That's just so we're reading the word color effect, not doing anything to it. And then we're going to take this, which we're loading from CImage1, and we're going to save that data at a new voxel position, which includes a double buffer, and CImage2 colored light. That's our color effect. So this on its own shouldn't do anything. It's just moving the data from one image to another, but then nothing happens to it. So if we load, okay, it didn't crash. That's good. Let's look now in our debuffer's train, and let's do something with it. So let's go down here to visualize data 5. This is what we want to do in the end. Let's go through this step by step. Now, we want this to be a smooth effect, not a blocky effect. So we need a smooth sampling position, whereas before when we did sampling for voxels, we were sampling at our voxel position, which was defined as an IVEC3, which means it doesn't have those decimal points of our foot position. And it looked like we were, or we could just take the one we had, or we were reconstructing it. So that was like a sharp once per block. We don't want that. So instead, we're going to create a smooth sampling position. So a smooth position, we take the foot position, we take off that fractional part of the camera position, so that we don't have sliding, and we add the voxel radius so that we sample based around the person, around ourselves. If we didn't have the, well, we can go over some of the bugs in a minute. We have to account for a double buffer offset. We do not read from the read position, we are reading from the write position, because we want to read what was written this frame, not what was written last frame. And we wrote to the right position. I just haven't named this so that it is, this code is just directly copied from our prepare compute shader. It's literally just the same line of code as we want to take from that spot. So we're going to read from this new image that we created. So we have our smooth position, or double buffer offset, and we're going to say that our position for our colored lighting, where we're going to read it, is our smooth position plus our offset. We're making sure this is a vec3 instead of an IVEC3 because this needs to be smooth. And then we're going to sample our effects. So we're going to say that our bytes, our 4 channels, is going to read from texture 3D, colored light, at this position. Now, because this is before, when we read our voxels, we were reading them from IVEC3 positions, and we were... Actually, no, it looks like we were doing this for the graphs the same way, so I don't have to go over that. But if we were using image load, we would just load at integer values. But if we're loading but from a sampler, it's a 0 to 1 range, so the position is over the entire range. We're not sampling at voxel 1, 2, 3, 4, 5. We're sampling at between the left edge being 0 and the right edge of all of them being 1. It's just a gradient from 0 to 1 in between. So our position is, to have that, we have our position over the entire size of the area. But because we have a double buffer, this size isn't just the voxel area. It's a voxel area on one axis. It's a voxel area times 2 on one axis because that's twice as big. And then it's this voxel area. So the way that would work is if you try to visualize it, this is the size of the entire image. So when we sample 0 to 1, it's going to sample the whole thing. Unless we say that our position is, like, it has to be aware of that extra thing. So it only samples, like, in one chunk at a time. So we have a 0 to 1. So it needs to be aware that, like, it's twice as big. And then to apply our colored effects, because we're applying them, we're going to first just do one of these. Is let's say that our red and green value should add our bytes.r. Bytes.r is what we have saved on there, which means it's the data that we voxelized passed into the buffer. So if our bytes.r is greater than 0, it should be a gold block. So we're going to have that add yellow to it because red plus green is yellow. And Let's see if that does anything. And it does. On our block there, we have yellow being added to a block that is gold. So it looks like the data is being voxelized, and it is being passed into our other buffer, and we are sampling it correctly. Let's now look into our prepare, and let's start doing something with this data instead of just having it. So let's have some fun with it. Let's look at what I've got here, and we'll do our flood fill type effect. Now, a flood fill, the general idea of it is that we want, this block to light things up around it. If we have a big square here and we want it to light up 15 blocks in every direction, let's just say 10 for easier math. How many blocks would you have to sample to know how much light is right here from this? How would it know to check that spot? Well, unless you want to sample every block that's within 10 this way, 10 this way, 10 this way, and 10 this way, that square is a 10 by 10, a 10 by 10, it's 100, that's 400 blocks just in 2D. If you do that in 3D, that's like thousands of blocks. That's too many blocks. You can't do that. So what Floodfill does to make this easier is it pre-calculates the lighting for whatever effect we're doing. So the effect from the gold block is that it's lighting up blocks around it. And the way we're going to spread this is in each frame, instead of having to check thousands of blocks to see if any of them are light, we're going to propagate the light outwards. So we're going to say that in every move, in every frame, it's just going to go in these 4 directions. We're not using the Z value, or I guess it would be blind Minecraft. We're just going to propagate in 2D, and you could easily change this to 3D by just adding another bit. We're going to say in the first frame, it should just go 1 block here, 1 block here, 1 block here, 1 block here. Then in the next frame, you want to read not just what's emitting light, but what light is in that area, and have that light go to the left, the right, the north, the south, the east, west, whatever. So then over frames, it will slowly spread out, but that will happen very quickly to our eyes because the game is running very quickly. So let's look at how would we do that. We need to sample our neighbors and take data from them. So we already have our color effect is just the data from our primary voxel map, but we also save this data then to our secondary voxel light. So we want to sample our neighbors. So we're going to make an iVec3 because we're sampling a whole block over, and that's our neighbor. And then we're going to say that our new value of light, we're going to load the light value from voxel position old plus neighbor. So we're sampling the light from last frame, and we're off to the side. And we're going to say our total light, we're going to take the light value that was in that frame and minus 1/15 so that it only goes 15 blocks over. And let's try just that first, just sampling one neighbor, and let's see what happens to our stuff. We then also need to do something with total light. And light, we don't do anything yet. So we'll say color effect, excuse me. And this line here was just a debug line. You might have something like this be valuable when you're first doing this to make sure that you're actually reading your textures correctly. So if I do that debug view, it doesn't do anything. Color effect equals green. Oh, because green didn't do anything. We're only checking for a red value in our other shader. So if and then making things yellow because of it. So if I do this, boom, everything is yellow. So that means we are reading our textures correctly, which we already are. But in case you were having trouble knowing if the texture was actually reading appropriately, just write a set value to it, and you can get there easier. So we have our total light, and then let's do something with it. We want to make sure that because we're fading, we're doing negatives added to it. So there's a possibility that if there was 0 there, this would be a negative number. So let's say we take the maximum between 0 and total light, or total light, so it's not negative, and then say that our color effect should be whatever is greater, color effect or the total light, with color effect being the effect that's there from the primary voxel map, and the total light being all the total light from neighbors. Right now, we're just checking our neighbor to one side. So let's go back from here and see if we can do that, or it's shooting off to the side. And because we have that fade, it only goes so far. If we didn't have this fade, this would just go infinitely off in that direction. So let's look at that real quick. And it just goes off in that direction infinitely. And you can see we've got the smoothness because we are doing the interpolated read. If you're doing this from scratch on your own, be very aware of your sampling with all the double buffer stuff that we're reading from the right one. If you did this to the read instead of the write, for example, and I did this at first, you would get all kinds of jitteriness that will take you a while to debug. I want to show you that just so you see it. Actually, it looks like I never declared it, so it's, if I did the wrong one, it would be equal to this. I'll just show you what that would look like. You see that kind of thing there where when it's changing, it's not aware of it. So if you get something like that, that's what you messed up. And the rest of this, I think we covered in the voxelizing tutorial. So we got that back. So what else can we do with this is well, we wanted to fade it. And then we also want to check in the other direction. And let's say that, let's load our light value again, and say the total light will be whatever is greater, the light that we already loaded here or the light from the other side. So let's see what that looks like. And this should now go in two directions. So that's pretty cool. And let's go back in here and let's also sample in some extra directions. And there we go. Now, if you're doing colored lighting, you would also then have this go up in the third dimension. And you would also probably have it not go through walls. You would have it check for stuff like that and do some kind of logic for that, which we're not doing here. This is just the basics because this video is too long already. So let's do something else with this for fun. Let's go back into our compute shader and let's look at whatever code we have here. For example, is a slime effect. So for our slime effect, let's look at our voxelizing, and we were saving to our green channel if it was a slime, which we check by if it's an entity and the entity ID is 1, the green channel. So in our prepare shader, let's do a slime effect. Let's override the light value of our slime because we don't want our slime to spread out in every direction, do we? We want to just draw green slime where it is. So first, let's go into our fragment shader and let's draw the effect of our slime. Let's say that our RGB color should be a mix of what it is and green, because those are red, green, blue. And we're doing some math on it here. Let's get rid of that math for a second. And we'll bring it back. And say that we're going to mix from our color to green based on the green value of the data from our texture. So, oops, I'm in the wrong spot. Now with our Floodfill off of the slimes, that's really big. We don't want them to actually Floodfill. We're just using the same data channels, the same texture, to hold different things. I confused myself in my matrix of inception there. So in our compute shader, instead of taking a Floodfill value, let's instead for our green channel, just ignore that by saying that we want our green channel of total light to just be what was in that spot already, not what was in the neighbors, just what's in the original spot. And so this is a very wasteful way to do this, but we're just doing it this way. And then that should make it persist, where it is sampling only what was there from the frame before, and it's not spreading out in any direction. So there we go. You see that once a slime is in a spot, that spot is flagged as green, and then that spot in our compute shader just always reads what was green last frame and puts that into the new frame. So they make something a mess, and it just stays a mess forever. So what we can do is we can then fade that data by saying our total light green, we want it to minus 1 over 255, which is the lowest. Since there's 255 units in an 8-bit value, the smallest we can take off is 1 out of 256. So if we say our total light green should be itself, minus equals means itself minus 1 over 255, we'll get a fade. So let's look at that fade. And here, when we go somewhere with fades, that faded too quickly for me. I didn't like that. I wanted it to stay longer. So how would you make it stay longer when you can only minus 1 out of 255? Well, you would only do it every so often frames. So if we take mod frame counter 10, we're counting our frames to only go once every 10 frames. Only once every 10 frames, but that equals 0. So when we're on the 10th frame, we say that we should do this. So now only once out of every 10 frames will it fade. It sort of fades very, very slowly. Now also that effect is wider than I wanted, which is why if we go up here and we look in the stream, I was taking the effect and saying that I want to apply it with a power to 2, which will make it smaller, and then multiply it to make it brighter where it is. So make it be in less space, but be stronger. And if we do that, the effect that we get, if I save it, but it doesn't go out to the side quite as much, but it's kind of strong as it is. So let's look at the water. The water is pretty much doing the same effect because it's just taking a floodfill value, but we're going to interpret it differently because we did a floodfill on our red, green, and blue channels. Our green channel, what we're doing in the compute shader is overriding that to just slowly fade. So our red channel for the gold value is flood filling outwards. Our green channel is taking what was there last frame and just slowly fading it. And our blue value is just also just doing a flood fill, but we're going to interpret it differently. So we're going to take our water edges and we're going to, if they are something, so they're greater. Well, before we do that, let's just look at this, how it would be. I'm going to just show a way to play with data to make it look different. I'm just doing anything, so let's click what we're doing here. We're sampling our neighbors. We're mixing. So we're taking a color effect is equal to the data that was originally there in our main thing. We're checking the neighbors and taking a fraction of theirs to spread it out. And making sure it's not negative. We're taking whatever's greater, what's caused directly, or what's from the neighbors, outputting it. That should be good. So let's look at our voxelizing, make sure that we're doing this right. If an entity is 10,003, we save it. So let's look at our block.properties and make sure that we have that right. Number 3 is water, or Minecraft water, but the Minecraft isn't applied. So that should all be right. So if this is not doing what we expect, it is something wrong in the fragment shader where we're applying it. But because this number right here to the 11 is a very strong exponent. So let's just look at this more directly. Okay, so here's a flood fill coming off of our water. That's not at all the effect that I want here. I want to just get a little bit of a shoreline so we could do some cool beach effects, have the sand look wet or something. So we're just visualizing this as blue here. Now, I don't want it to go that far out, but I want it to go out some. So if I do a power, it takes that straight line and does it multiplied by itself, which if we remember from our math, if you take from 0 to 1 on a graph and you do it times itself, it gets smaller like this. And the bigger that power is, the more it goes like this. It has less range. It has to be closer to 1 before it actually kicks up. So if we take this and we go into our code and we so that we want this to be like 4 or something, then that line shouldn't go out very far at all. Excuse me. Actually, you can see it's just right there on the edge. Just going up that little bit on the edge of the block, going up. But we want it to kind of come out a little bit, just not as far as it was. So if you play around with the math, you can kind of get something less. But I want it to be, if it's anything, so it's greater than 0.001 because of flow precision. I don't want to just check 0. Let's add half to it. Otherwise, it'll probably be the same. And that gives us so that it'll pretty much extend out past itself a block, because I want this full effect on the next block over. Because if the full effect is just in the middle of its own block, like where the gold's full effect is only in the middle of itself, it won't make the neighboring tile look wet. It'll already be at like half by the time it gets right there. But I want it to be 1 there, so that's where we take its value and add a half to it so that the edge of the next block is fully blue. And then that's why I've got this power to be really strong here. And then it fades off very quickly. And then we could do something else with that. If we're doing this in a PBR shader, we could do something with wetness or add like a noise texture to then have it be like puddles. Maybe have waves wash up control. You can do whatever you want with that. We're just saying this is another way to interpret that data that we spread out on the water. And I think that's it for this tutorial. So let's look over like a bit of a review of what we did. Is we passed data from our voxelizing into a separate 3D texture, which then runs stuff on it in a compute shader. What it runs is sending out a floodfill by having data send out into its neighbors every frame, so that instead of having to sample thousands of blocks to tell if there's a light block, a gold block nearby, it literally just checks right where it is, because the values slowly spread out over every frame. If I slow down my frames even slower, you might be able to see that. There we go. You can see how every frame it's checking the neighbors, so it goes out every frame. And then we have that's pretty much the same code happening from the gold and the blue. And the green, it's just taking what was their last frame and making it smaller once every 10 frames. But it's taking what was their last frame from slime, and it's also taking what's their newest frame from the primary texture, which is the slime block itself. So again, our actual compute shader, we were declaring our version because you have to do that first. We're making our settings because we don't use the settings GLSL file in this tutorial. We set our local size to be 8 by 16 by 1, which is 128. 256 is probably better. We are making sure there are enough of those work groups, this is how big they are, enough of them to fill in our whole voxel map based on how big it is. We are setting, we're loading in from our primary voxel map, which we declared in shader.properties. We have our floodfill image, which was also declared in shader.properties. We are writing to it and or reading to it, so we have it declared this way as an image. And then we use a frame counter to help our double buffering, and we use the 2 camera position things to tell when we've moved, so we can move the data over from the last frame. We are wrapping this in define so that we can disable these one at a time in case we do like a whole bunch of them in one thing. We get the index of our thread using GL global invocation ID, and we are adding our camera shift and our double buffering so that we have a position to read from and to write from. We are making sure that we are in the voxel range, that we don't waste in case our work group size couldn't perfectly match what we needed. So we load from our primary voxel map to see if this block triggers an effect, unpack the data, and set that as a color effect. And then the stuff we're doing is we're doing our Floodfill by checking neighbors and seeing how much they contribute to this block as well. And then making sure that our fade does not go negative, so that our color effect should be whatever's brighter, the light that we already have here from the primary voxel map, or whatever's coming from the neighbors. For our slimes, we override the G value since we're using this buffer not just for Floodfill colored lighting, but for 3 different things at once. And then when we output our data, we're using image store, and we're saving to our colored light, which is our 3D texture that is double buffering, add our new position, setting that color effect. In our voxelizing.glsl, we just added that visualize data 5, or these Floodfill type effects, is saving a different thing for each of the blocks we wanted to do an effect for. And then in our debuffer's terrain, our visualize data number 5. First of all, we didn't just visualize voxels, we kept textures, unless if we were doing 5. And then for 5, we take a smooth sampling position. We account for our double buffer, and then we load in the bytes from our new texture, a new 3D texture, as a sampler, so smooth sampling. And then we applied an effect for each of the blocks we wanted an effect to have. That's it. That's how we played with computer shaders and looked at that stuff. And again, you could do anything else you want in here. Like I said, this is like 2 steps away from being a perfectly competent Floodfill lighting system. You could do the rest. If you watch the voxelizing episode and you watch this, and especially if you've done any of the other tutorials, you've got a little bit of a handle on logic. It should not be hard at all for you to take this to the next step. But I think this is a fun way to show this. And sorry, keeping the screen kind of shrunk half the time. I didn't even think about that. But I hope you had fun with this episode, even if these effects on their own aren't especially impressive. The point of them is just to show you a visual of some stuff you could do with data. So we can have a block affect blocks around it. We can have a block affect things in like a semi-permanent manner. Once we leave the area, it would probably be gone. And we can do area effects that voxelizing allows us to do by using compute shaders to do it efficiently. Because if this block had to check every block around it, it took thousands of blocks, it would not run at any good FPS. But by only having to check a few, only having to check exactly itself, and then get a nice smooth gradient, I think that's a pretty good move. So I hope you had fun learning about compute shaders, and you had fun taking your little guys and putting them into little 3D workgroup formations so that they could do work for you and you could make some cool effects. Let me know what you guys do with this information and what kind of effects you make. And again, thank you to everyone who supports on YouTube and Patreon. If you appreciate these tutorials or any other stuff, you can subscribe or leave a tip on Patreon. If you want to complain about my microphone quality, you can tell me which budget microphone you recommend and leave a tip so that I can afford it. But have fun, everybody. I hope you create some cool stuff. Let me see what you make, and I'll talk to you soon.